Hello, my name is Sanad, and today I will be talking on behalf of my team about a project that we have been working on for the past 4 weeks. This project was based around the bridge which goes from Building A to Building K at the Victoria University facility as seen on the screen. The project was split into 3 phases, which are bridge design, phase 1, followed by load analysis, phase 2, and lastly internal forces, phase 3.
Hi, my name is Sadri. In this video, I'll be discussing Phase 1, the bridge design. This phase is all about the different structural members that make up the bridge. These structural members include 6 reinforced concrete columns, 3 lateral beams, longitudinal beam small section, longitudinal beam large section, railing, and the 6 brick columns. In total, the bridge is 17 meters long in length and 7.3 meters long in width. The 6 brick columns around the reinforced concrete columns are 59 centimeters in thickness, and the 6 reinforced concrete columns on the inside are 35 by 35 by 2,350 mil. The bridge's total height is 2,350 mil. The 3 lateral beams connecting the columns to hold the slab up are 760 centimeters in length, 35 centimeters in width, and 74 centimeters in height. The 3 longitudinal beams are 570 centimeters in length, 35 centimeters in width, and 74 centimeters in height. Surrounding the outside of the bridge are 5 safety railings. These railings are 730 centimeters in length, 10 centimeters in width, and 124 centimeters in height. We as a group were able to establish these measurements by measuring each component 3 times, then dividing it by 3. Then we had to work out the uncertainties by subtracting the lowest value from the highest value, then dividing it by 2.
We also worked out how to find the density of each element within the bridge. We also found out the volume of each beam, which is found out by multiplying the length by the width and by the height. As we multiplied the density and the volume, this found out the mass of each section of the bridge. The first section of the bridge we calculated is a longitudinal beam. The longitudinal beam is made out of steel, meaning it has a density of 2,400 kilograms per meter cubed. The volume of the longitudinal beam is 4.247 meters per cubed, which resulted in a mass of 10,192 kilograms. The second section of the bridge we calculated is the lateral beams, which there are 3. The lateral beam is made out of steel, meaning it also has a density of 2,400 kilograms per meter cubed. The volume of the lateral beam is 1.891 meters per cubed, which equals a mass of 4,538.4 kilograms. The third section of the bridge we calculated is the concrete slab. The concrete slab also has a density of 2,400 kilograms per meter cubed. The volume of the concrete slab is 50.28 meters per cubed, which resulted in a mass of 120,672 kilograms. The last section we calculated is the rails. The rails has a density of 7,700 kilograms per meter cubed, which resulted in a volume of 1.347 meters per cubed and has a mass of 10,356.5 kilograms. As we added all these sums up, the total mass of our bridge is 145,759.7 kilograms. Hello, my name is Marcel, and I will be discussing phase 2 of our project, which is the load analysis. This includes the dead loads, live loads, and the reaction forces of our bridge. In order to find the live load, we had to find the pressure, which is stated in the Australian standard 1170.1, which gave us a pressure of 5.0 kPa. This was used to find the live load as we multiplied it by the area of the bridge, which was 5.74 meters. This resulted of a live load of 598.6 newtons. The dead load was found by multiplying the mass of the bridge, which was 145,759.7 kilograms, and multiplied it by the gravity. After that, we divided it by 1,000 in order to get a result of 1,457.597 kilonewtons. The UDL we found by the mass times the gravity and divided it by the length of our bridge, which is 16.4, gave us a result of a UDL of 62.68 newtons. This was used to find the reaction force of the middle column, which was 695.14 kilonewtons. This was given by a teacher, since it helped us identify the reaction forces for the small section of the bridge, 5.7 meters, and the large section of our bridge, 10.7 meters. To find these, we had to divide the load acting on the bridge by 2, which gave us a value of 1,028. We then multiplied that by half of the bridge, which is 8.2 meters. Then we minus that by 10.7 meters, and then times that by the length of the bridge, which is 16.4 meters, to find the reaction force of the small section of the bridge, which was 59.35 kilonewtons. To find the reaction force for the large section of the bridge, we multiplied 1,028 by half the bridge, which was 8.2 meters. Then we minus that by 5.7 meters and times that by 16.4 meters, which is the length of the bridge, to find the reaction force of the large section of the bridge, which was 273.46 kilonewtons.
Hello, my name is Sanad, and today I'll be talking about internal forces in Phase 3. Within any structure, there will always contain forces acting upon it, such as the self-weight of the item and also any live loads acting upon it. Within Phase 3, we were required to submit calculations of the shear forces and bending moments. With our calculations, we were required to construct a diagram of the shear force and bending moment acting upon our bridge's beam, as shown above. The shear force from the large section of the bridge is 273.46 kilonewtons. The bending moment, 596.52 kilonewtons per meter. For the small section of the bridge, the shear force is 297.92 kilonewtons. The bending moment is 45.91 kilonewtons per meter.